Welcome to Essential Problems of AP Chemistry. Given the prompt, calculate the nuclear binding energy per nucleon for any given isotope, you will need the given isotope and its atomic mass, a chart of the weights for each subatomic particles that you will use, and the equation change in E is equal to change in mc squared. Now in this case, we're going to take the nickel 62 isotope weighing 61.928 grams per mole. There are certain key ideas that will make things easier, and the first one is to understand your units. Take, for example, the molar mass given. 61.928 grams is how much 1 mole of nickel 62 atoms weigh. If we actually convert this to AMU, given the definition for 1 mole and the equivalence of 1 AMU to 1.66054 times 10 to the negative 24th grams, we will find that one atom of nickel 62 weighs exactly 61.928 AMU, atomic mass units. Now, what's important here is that you understand grams per mole does not equal AMU. You must understand this. However, the system of conversions was created so that we could easily, once we know one of these values, know the other due to this relationship. So if you know grams per mole, you know the AMU, the atomic mass units, for that given particle. And if you know the atomic mass units for a given particle, you know its molar mass. So continuing to the right, if you're given a neutron weighing 1.008665 AMU and a proton weighing 1.007276 AMU, well, then that means that if you had 1 mole of neutrons, well, the molar mass of a neutron would be 1.008665 grams per mole of neutrons. And same thing with a proton, and same thing with an electron. Again, understand AMU and grams per mole are not the same, but understanding the relationship makes the value conversion incredibly easier. Now, the next key idea you need to understand is what you are solving for. It is reported, or at least we're being required to report it, in joules per nucleon, energy per nucleon, okay? And this is typically done to make the comparison between these isotopes easier. So we are going to solve for nuclear binding energy per nucleon in joules per nucleon, okay? So this is the energy that would be released to form one atom from its subatomic particles. So let's kind of create a reaction, a nuclear reaction, although this is not exactly how it takes place, but it helps us to understand our calculation. We have on our initial side 28 individual protons and 34 individual neutrons. How did I figure out this? This is nickel 62. We can look at the periodic table and determine the number of protons on the periodic table for nickel, and that's 28. Subtracting from 62, we get 34. Of course, for a stable atom, there are 28 electrons. So we have the components separate on the initial side, and then on the final side, we have one whole nucleus made of 28 protons and 34 neutrons, plus the 28 electrons that would be bound to that nucleus. Now, another key aspect of this problem is that all of the energy released in this nuclear reaction comes from forming the nucleus, not the electrons. It is not required. We can just simply eliminate the 28 electrons on both sides because they won't affect our calculation. So let's begin the solution. Change in E is equal to change in mc squared. C is a constant, so we shouldn't be focusing on that. We should be focusing on the change in mass. And any change will be final minus initial. So mass final minus mass initial. We should further define this. Now, we have been given in this case the molar mass of the nickel 62 atom. Okay? And we've already established the relationship that we can use that numerical value for AMU. So the atomic mass of just one atom would be 61.928 atomic mass units. Okay, so should we use AMU or grams per mole? Well, we've been asked to solve for energy per nucleon, which is a tiny, tiny, tiny unit. We don't want to use the big relationship, we want to use the small relationship. So it's easier to solve this problem using the atomic mass unit. Now, if we use the atomic mass unit, right, then we also have in that atom still 28 electrons. So we have to be careful here. When we are saying mass final, we just want the mass of nickel 62 nucleus. So we need to take that mass of the nickel 62 atom and subtract the mass of 28 electrons in order to get the total mass final. Of course, mass initial is just the mass of all of those protons and all of those neutrons separately. Note that I am not including the mass of electrons in this case. If I were to do this, I would actually have to add mass of 28 electrons additionally to that mass final section and also to the mass initial section. Now, that might be easier for some of you to do. You'll notice then that the negative mass of 28 electrons plus the positive mass of 28 electrons would cancel out. So you would just get the mass of the nickel 62 atom minus the mass initial, which would be the mass of the 28 protons plus the mass of the 34 neutrons plus the mass of the 28 electrons. You can do that. Again, there's actually not much difference. The math would be exactly the same. But the takeaway here is that you should set up algebraically everything with full understanding before you substitute and do the math. Now, once we start to substitute, we should keep things organized and simplify, writing the values underneath. And then once we get to the end, notice that I underline where the correct number of sig figs should be rounded to at the end. Once we've done this calculation, change in the m is equal to negative 0.5855699 AMU, and this is the mass defect, the mass that has been lost from the nuclei. The mass that has been lost in forming that nucleus. Now, given that change in m, the rest of the calculation becomes pretty straightforward. One thing we do need to note is that the value needs to be in kilograms in order for us to get units of kilograms times meters squared per second squared, or equal to a joule. So we do need to convert that AMU to kilograms using the conversion provided. Then we need to multiply that by the speed of light squared. Once we've simplified this value, we now have joules, the energy that was released because it is a negative value. But it's the joules that has been released per nucleus, per nickel 62 nucleus formed. Now, we were required to report this in energy per nucleon. And so we need to recall that a nucleon is either a proton or a neutron. So nickel 62 nucleus has 62 nucleons. Once we write our units, joules per nickel 62 nucleus, we can see that the conversion is pretty straightforward. That is 1 nickel 62 nucleus to 62 nucleons. We must divide by the 62 nucleons. And so we get joules per nucleon. But what if we were asked to report the value in joules per mole of nickel 62 nuclei formed? Notice how the conversion is significantly different. We again start with joules per nucleus, like we did, but since we are kind of zooming out, we have to multiply. Of course, this is easy to see. if we're using our units to guide us. Since we're a nickel 62 nucleus, we can only go from nuclei to 1 mole of nuclei. And so if we multiply by Avogadro's number, we get joules per mole of nuclei formed. The takeaway here is that if we were to be given a nuclear reaction, the calculation for this problem would not be any different. Signing off, Crip.